We're going to end this chapter on factorization with a section on reducibility tests, ways that we can quickly tell whether a polynomial over a field or over a unique factorization domain is irreducible or not. So let's start with Theorem 145, which tells us of a way that we could check for reducibility of polynomials of small degree. And it says if R is a unique factorization domain, F is its field of fractions, and little f inside of the polynomial ring over R, f inside R join x, is primitive, then f is reducible in R join x if and only if f has a root in f. So note that the field of fractions of a field is just that field back again. And so this theorem is often stated just for polynomials over a field, but by corollary 140, we can state it in this slightly more general form. So by corollary 140, since we know that f is primitive, f is reducible in R join x if and only if f is reducible in the polynomial ring over the field of fractions f itself. So we're sort of reducing to the case where f is a polynomial ring over a field. So we're going to show that all this holds if we were just looking at polynomial rings over a field to begin with. So let's suppose that f inside the polynomial ring f adjoint x is reducible so that f is equal to gh, where g and h are non-units. Now, because g and h are non-units, that means that they're non-constants, and in particular, that means that they each have degree 1. So we have that the degree of f is equal to the degree of g times h, which is the degree of g plus the degree of h, and the degree of f is less than or equal to 3. And since the degree of g and the degree of h are both at least 1, and their sum is less than or equal to 3, we have that either the degree of g equals 1 or the degree of h equals 1. Without loss of generality, we may assume that the degree of g equals 1. Therefore, g equals a plus bx for some a and b inside f, where b is not equal to 0. But that means that b inverse a is a root of g, so b inverse a is a root of f. So we have that if f is reducible, then one of its non-unit factors must be a linear polynomial, and linear polynomials over a field always have roots. And so since the root of a factor of, since a factor of f has a root, f has that same root. So now let's suppose that f has a root a in f. We've already shown that in general, if you have a polynomial over a field and it has a root which is part of that, which is an element of that field, corollary 16, or 116, sorry, by corollary 116, x minus a is a factor of f. So f has a factor, so that means that f is equal to x minus a times sum g now since the degree of g, since the degree of f is at least 2, we have that the degree of g is at least 1, so g is a non-unit. Therefore, f is reducible. So that finishes the proof. If we can find a root of a polynomial within the field of fractions of the coefficient ring of its polynomial, of the polynomial ring it belongs to, then it is reducible if the function is degree 2 or 3. This is an if and only if statement. Now, when we are dealing with a unique factorization domain, we can sometimes simplify this process because when we're looking at polynomial rings over unique factorization domain, we can reduce the number of potential roots there are of our polynomial in the field of fractions to a finite number. So theorem 146, this is sometimes known as the rational root test, and you may have seen it in the context of polynomial rings over the integers. So let R be a unique factorization domain, and let's let f be a polynomial, a0 plus a1x plus a2x squared plus etc. plus an x to the n in the polynomial ring R join x, with an not equal to 0. Any root in any root of the polynomial f in the field of fractions f, which has the same meaning as in the last theorem, is of the form b over c, where b and c belong to the ring R, and b divides a0 and c divides a n. Now, the reason why this is helpful for us, the reason why this reduces the number of possible roots of the polynomial f, is because since R is a UFD up to associates, every element of R has only finitely many distinct factors. So this allows us to reduce the number of elements that we have to check significantly. Although I should say, if the ring R has infinitely many units in it, then it doesn't necessarily bring us down to a finite set of units, a finite set of potential roots to check. But it's still much smaller, a much smaller collection of things to check than the whole field. Let's see the proof. Let's let b over c be a root of little f in the field of fractions f. Now, since b over c lie in the field of fractions f, they have all of the standard properties of fractions, including things like cancellation. So we may assume that b and c are coprime, meaning that their only common divisors are units. So we have then that a0 plus a1 times b over c plus a2 times b over c squared, etc., up to an times b over c to the n equals 0. We've assumed that b over c is a root of little f. So now, if we multiply both sides by c to the n, we get that a0 times c to the n plus a1b times c to the n minus 1 plus a2b squared c to the n minus 2, etc., plus an b to the n equals 0. Now what you'll notice here is that c divides the first n terms of the sum and the right-hand side. Everything divides 0. There's at least one factor of c in each of the first n terms, all of them except the last one. So therefore, c divides a to the n times b to the n. Now, since c and b are coprime, c does not divide b. In fact, no irreducible factor of c divides b to the n. So, since c divides a to the n, b to the n, and any irreducible factor of c, it can't divide b to the n, so it must divide an. Since this is true for all irreducible factors of c, we must have that, therefore, c divides an. A perfectly symmetric argument shows that b divides b0. A0, sorry. All right, so let's take as an example the polynomial f, which equals 3x cubed plus 2x squared minus 5x plus 8, which is in the polynomial ring over the integers. We want to show that this is irreducible. Since it's degree 3, we can do that by showing that it contains no rational numbers as roots. No rational number is a root of this polynomial. Now, if we had to check all rational numbers, of course, that would be very difficult, but we can do better by using the previous theorem. So first of all, notice that f is primitive. So f is irreducible if and only if it has no roots. Therefore, by theorem 146, or it has no roots in Q, I should say, the field of fractions of Z. By theorem 146, any root of f in Q is of the form b over c, where b divides 8, the degree 0 term of the polynomial, and c divides 3. So that means that b could be plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8, and c could be plus or minus 1 or plus or minus 3. And so we can look at all of the different ways that we could combine them together. And we can check to see that no matter what value of b or c you take, that fraction is not a root of f. So for instance, we could say, well, we could take b to be 1 and c to be 1, or we could take one of them to be -1. So we could take f of plus or minus 1. It turns out that f of 1 is 8 and f of -1 is 12. And really all we're checking here is to see that they're non-zero. So we could take b to be 2 and c to be 1, and then plus or minus that. That gives two non-zero numbers. It gives 30 when you for positive 2, 2 for -2. F of 4 is 212. F of -4 is -132. And f of 8 is 1632. F of -8 is -1360. All right, so these are all the possible numbers we can get with a c value of plus or minus 1. So then we can look at f of plus or minus 1/3, and that gives us 20/3, 88 ninths. F of plus or minus 2/3 gives us 58 ninths and 34 thirds. F of plus or minus 4/3 gives us 12 and 100/9. And then f of plus or minus 8/3 gives us 592 ninths and -64 thirds. So there are only 16 possible rational numbers that could possibly be roots of f by theorem 146. If we check all 16 of those numbers, then we find that none of them are roots of f, and therefore f is irreducible. So in corollary 140 and these things that we've done here, we've tried to check the irreducibility of f by looking at a larger coefficient ring. We've thought about polynomial rings over the integers and thought about, oh, what happens if we think about these as rings over, as polynomials over the rational numbers, and moving from a ring to its field of fractions a lot of times. Sometimes we want to go the other way. So we want a sort of general idea of what it means to change the coefficient ring of a polynomial, which is going to be built using ring homomorphisms. Theorem 147 gives us the framework that we need. So let's let R and S be commutative rings. And let's let phi from R to S a ring homomorphism. We can define a function, which I'm going to call phi bar, that goes from the polynomial ring in one variable over R to a polynomial ring in one variable over S, which is given by the following. Phi bar of a polynomial, a0 plus a1x plus etc. plus anx to the n, will be the polynomial that we get in S by applying phi to each of the coefficients. So it's simply applying the homomorphism phi to each one of the coefficients of the polynomial. So technically this is what we're doing when we move from a polynomial ring over a domain to its field of fractions. In that case, the homomorphism that we're using is the ordinary inclusion homomorphism that takes an element and takes it to the fraction of that element over 1. But this we can do that process with any ring homomorphism. Okay, so finishing the sentence, the function phi bar defined this way is a ring homomorphism. Between the polynomial rings R adjoin S and S adjoin S. Also, we have that phi is injective, respectively surjective, if and only if phi bar is injective, respectively surjective. So, for instance, when we move from a ring to its fraction field, that's an injective homomorphism. And so when we move from a polynomial ring over a ring to a polynomial ring over its fraction field, that is also an injective ring homomorphism. Now, there's a second part to this theorem. If R is a unique factorization domain, so more specific, phi is surjective, the degree of phi bar of f equals the degree of f, and phi bar of f is irreducible in S adjoin x, then f is irreducible in f adjoin x, where f is the field of fractions. Of R. Now, the fact that this gives us reducibility in f adjoin x rather than R adjoin x is of course not an issue because of corollary 140, which says that if little f is primitive, then the reducibility in R adjoin x and f adjoin x are equivalent. All right, for the proof, the first part, the first paragraph of the statement is an exercise. Proving that phi bar there is a ring homomorphism and that it's injective if and only if phi is injective, and surjective if and only if phi is surjective, is a straightforward exercise that we've done several times before. You can do if you like, but there are really no wrinkles that show up in it. So let's prove the second part, and we're going to prove the contrapositive. So let's suppose that R is a unique factorization domain, phi is surjective, and the degree of phi bar of f is equal to the degree of f. I should notice that because phi only takes 0 to 0, the degree of phi bar of f can never be larger than the degree of f, but it can be smaller. If phi bar sends the leading coefficient of f to 0, then the degree of phi bar of f will be less than the degree of the degree of f. But part of our hypothesis here is that the degree of phi bar of f is actually equal to the degree of f. So now, the conclusion in the statement of the theorem was that f is irreducible in f adjoin x. So now let's suppose that f is reducible in f adjoin x. And what we're going to do is we're going to show that f is reducible in s adjoin x. So since f is reducible in f adjoin x, by the proof of corollary, I should have specified in here, and I should have specified in the statement of the theorem perhaps also, f is a polynomial in R adjoin X. Let me check that and correct that. Yes, I should have specified here what F is. Shouldn't reference that symbol without defining what it is. So by the proof of corollary 140, since F is an element of the polynomial ring over R, and it's reducible in the polynomial ring over the field of fractions, we can do this this manipulation where we multiply by the least common multiple of the denominators and then compare contents and so forth and so on. So by this proof, F is equal to G times H for some G and H in R adjoin X, and where the degree of G and the degree of H are each at least 1. So if F is reducible in F adjoin X, then that means that F is then that means that we can do this by following the steps in the proof. So then, since phi bar is a ring homomorphism, we have that phi bar of F is equal to phi bar of GH, which is phi bar of G times phi bar of H. Now we have that the degree of phi bar of F rather, is equal to the degree of phi bar of G times phi bar of H, which is less than or equal to the degree of phi bar of G plus the degree of phi bar of H. The degree of a product is less than or equal to the sum of the degrees of the originals. Remember that we haven't assumed anything about S at all except that it's a commutative ring. It might not be a domain, it might not be a unique factorization domain. We know nothing, so all we can say is that the degree of a product is less than or equal to the sum of the degrees of the factors. But we also have that the degree of phi bar of G is less than or equal to the degree of G. As I said, the function phi might send the leading coefficient of G to 0, so the degree might drop. But we also have that the degree of G is less than the degree of F, which is equal to the degree of phi bar of F. And we also have that the degree of phi bar of H is less than the degree of phi bar of F. Therefore, since these two degrees, the sum of the degrees of phi bar of G and phi bar of H are each less than the degree of phi bar of F, but their sum is greater than or equal to the degree of phi bar of F, we have that the degree of phi bar of G and the degree of phi bar of H both have to be at least 1. Neither one of them could have degree 0. So this means that neither phi bar of G or phi bar of H are units. Hence, F is reducible in S adjoin X. And that finishes the proof. So, if S is irreducible, if we can find any commutative ring S where when we send our polynomial F to the polynomial ring S adjoin X and it becomes irreducible there, then that automatically tells us that the polynomial rather is irreducible in the polynomial ring over the fraction field of F. Now, there's one place where we use this this sort of idea, this sort of passing to another ring using a surjective homomorphism very often. The most common application of Theorem 147 is when R is the integers, so we're looking at a polynomial ring over the integers, and S is a field Z mod PZ where P is a prime number. This means that we take some polynomial f, a0 plus a1x plus dot 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 plus an x to the n, and we send it to a0 bar plus a1 bar x plus dot 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 plus an bar x to the n, where this polynomial lies in the polynomial ring over Z mod PZ. Now the advantage to this is that this is a field. Z mod PZ is a field, and so we can use things that we know about polynomial rings over a field to check for the irreducibility of f here. In particular, if f has degree 2 or 3, we can show that f is irreducible by showing it has no roots after reducing modulo some prime p. Now we do have to make sure that the degree of f doesn't drop, so it has to be some prime p which doesn't divide the leading term of f. The leading coefficient, I should say. So let's see how that goes. Consider the polynomial f, which is 6x cubed minus 3x squared plus x minus 9 in the polynomial rings over the integers. So to use the strategy in the previous example, we're going to want to reduce this polynomial modulo p, where p is some prime that doesn't divide the leading coefficient. Leading coefficient here is 6, and so the smallest prime that we might try reducing is 5. So let's suppose p is 5. We can say we can use the notation f bar to mean the reduction of f to a polynomial inside Z mod 5Z adjoin x. And when we do that, 6 is congruent to 1 mod 5, so we can just leave that as x cubed, minus 3 bar x squared plus x, and then 9 is congruent to 1 mod 5. So after reducing modulo 5, we get this polynomial here. You could, of course, put in the coefficients of 1 in front of the x's. This is also not the only way to describe f prime, because you have different representations of the various cosets in Z mod 5Z to work with. So now, since Z mod 5Z is a field, we could show that f is irreducible in this polynomial ring by showing that it has no roots in Z mod 5Z. Now, if we were working over the rationals, this would be difficult because we'd have a lot of things to check. However, the field Z mod 5Z only contains 5 elements. So we can see by brute force if f has roots in Z mod 5Z. We can take F bar of 0 bar, and it turns out that that gives us 0 bar cubed minus 3 bar times 0 bar squared plus 0 bar plus 1 bar, which gives us 1 bar. F bar of 1 bar is equal to 1 bar cubed minus 3 bar times 1 bar squared plus 0 bar plus 1 bar, which turns out to give us 0 bar. And we can check the others. But we don't have to. We can stop here. This tells us that 1 bar is a root of F bar. Since F bar has degree 3, we don't even need the degree consideration at this point. 1 bar is a root of F, so that means that F is reducible in Z mod 5Z adjoin X. However, unfortunately, this doesn't tell us anything. The implications of Theorem 147 go a specific way. We need to know that the polynomial is irreducible after reducing to S adjoin X. And knowing that F is reducible in this new polynomial ring doesn't actually tell us anything. So, unfortunately, this doesn't tell us anything. So, we could move on. Let's look at the next one. So, F is 6x cubed minus 3x squared plus x minus 9 inside Z adjoin X. And so let's try with P equals 7. If we reduce everything modulo 7, then F is, well, instead of writing 6, we could write negative 1 bar. That just makes the computations a little bit easier. Negative 1 bar x minus 3 bar x squared plus x plus 5 bar inside Z mod 7, 7Z adjoin X. Now, if this happens to be irreducible, then that will tell us that the original function, the original polynomial rather, is irreducible. And again, because F has a degree 3, we can do that. We can show that F is irreducible by checking to see whether or not it has roots inside Z mod 7Z. So we could do that. F of 0 bar is negative 1 bar times 0 bar cubed minus 3 bar times 0 bar squared plus 0 bar plus 5 bar, which is 5 bar. F of 1 bar is equal to negative 1 bar times 1 bar cubed minus 3 bar times 1 bar squared plus 1 bar plus 5 bar, which winds up being 2 bar. And similarly, if you work out the rest of them, F of 2 bar is equal to 1 bar, F of 3 bar is equal to 3 bar, F of 4 bar is equal to 2 bar, F of 5 bar is equal to 6 bar, F of 6 bar is equal to 2 bar. So what we've done now is we've checked all the elements of Z mod 7Z to see if any of them are roots of F, and none of them are. When you plug each of these into F and evaluate F at that number, you never get the 0 element out of it. You never get 0 bar out of it. So therefore, F has no roots in Z mod 7Z. And since F has degree 3, this means that F is irreducible in Z mod 7Z adjoin X. Well, now by Theorem 147, because F is irreducible in Z mod 7Z, that means that F f bar has no roots in Z mod 7Z, so f bar is irreducible in Z mod 7Z. That means that f is irreducible in Q adjoin X, because Q is the fraction field of Z. And then, because f is primitive, there's the greatest common divisor of all of its coefficients is just 1. Because f is primitive by corollary 140, that means that f is irreducible in Z adjoin X. So this method can easily be used to check to see whether can sometimes, I should say, easily be used to check and see whether polynomials of degree 2 or 3 are irreducible. If you have some other way of checking whether the polynomial is irreducible after moving to the ring Z adjoin X, that still works. We only need a degree 2 and 3 here in order to be able to check reducibility just by checking roots. So a reasonable question could then be, is there any is there a way to automate this, to use this as a way of checking any say degree 3 polynomial over the integers for reducibility simply by reducing modulo a bunch of primes? And unfortunately, that's not the case. There exist irreducible polynomials in Z adjoin X, which are reducible modulo any prime. For instance, x to the 4th plus 1 is an example. Now, it's not it's not totally obvious that x to the 4th plus 1 is reducible modulo every prime p, but it turns out that it is. That you can always factor this polynomial after reducing to Z mod PZ for any p. So unfortunately, it's not quite the silver bullet that we would like, but there do exist irreducible polynomials which are reducible modulo any prime p. Sorry, I misread my notes. This should actually be x to the 4th plus 10x minus 10x squared plus 1. I missed that middle term. Sorry about that. This polynomial turns out to be reducible modulo any prime, but is not irreducible in Z adjoin X. So we can use a similar idea to the proof of the previous theorem to prove our last condition here called Eisenstein's criterion. And it can sometimes give an extremely quick proof of the irreducibility of a polynomial, and this is specifically for polynomials over the integers. So Theorem 148, this is known as Eisenstein's criterion. And it says let f be the polynomial a0 plus a1x plus blah 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 plus an x to the n be a polynomial ring over be in the polynomial ring over the integers, and then if there exists a prime number p such that three conditions hold, P does not divide an, does not divide the leading coefficient. P does divide ai for I less than n, so it divides all of the other coefficients of f. And p squared does not divide a0, then f is irreducible over q adjoin x. And therefore, if f is primitive, then it's also irreducible over z adjoin x. All right, so let's see the proof of this. This is similar to, as I said, what we did in Theorem 147. Let's suppose there exists a prime number p such that p does not divide an, and p divides ai for I less than n. So let's assume that everything's true about this except for the last part. We're not going to assume p squared divides a0. We're going to prove a contrapositive here. So let's suppose that f is reducible over q. We will show then that p squared has to divide a0. So by the proof of corollary 140, again, there exist g and h in z adjoin x with the degree of g and the degree of h greater than or equal to 1, such that f is equal to gh, since f is irreducible over g. Now, we're going to want to refer to the coefficients here, so let's let g be b0 plus b1x plus blah, 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 dot, dot, plus b r x to the r, and h is c0 plus c1x plus dot, 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 plus cs x to the s. So now we're going to reduce to z mod pz for this specific prime p that we're working with here. So reducing to z mod pz, we have that f bar is equal to g bar times h bar, where the bars indicate reducing each of the, or sending each of the coefficients to the ring z mod pz. Since p does not divide an, we have that the degree of f bar equals the degree of f. P doesn't divide an, and so the degree of f bar hasn't changed, which equals n. Following a similar degree type argument here, because the degree of f hasn't changed, it hasn't gone down, and the degrees of g bar and h bar can't go up, they could only go down, it has to be the case that neither of the degrees have gone down. So that means that we must have that that the degree of g bar is equal to the degree of g, and the degree of h bar is equal to the degree of h. So everything keeps its same degree that it had before, which is good. So now let's look at what is actually happening with these polynomials. So since p divides ai for all I less than n, we have to have that f bar is equal to just an bar times x to the n, because when we move to z mod pz, all of the other coefficients will just become 0. Now, we have that the ring z mod pz adjoin x is a unique factorization domain. It's a polynomial ring over a field. It's a principal ideal domain, and therefore it's a unique factorization domain. And furthermore, X is an irreducible element. In it. So, since we have that an bar x to the n is equal to g bar times h bar, that means that the g bar and the h bar together must simply be powers of x with some coefficient. Because factorization into irreducibles are unique. If g and h had any other, if g bar and h bar rather had any other factors besides x, then those factors would show up in the factorization of f bar. But they don't. The only factors of f bar are x to the n and a unit, and so the only irreducible factors of g bar and h bar are x. Repeated x. So we must have that g bar is exactly equal to br bar times x to the r, and h bar is exactly equal to cr bar times x to the r. So in other words, all of the other coefficients of g and h must also be divisible by p, just like for f. So that means that p divides bi for I less than r, and p divides ci for I less than s. Sorry, this should be s is here for the for h. So that means that a0, which is equal to b0 times c0, the constant terms of f is equal to the product of the constant terms of g and h, and since p divides b0 and c0, so that means that p squared must divide a0. So p is a factor of b0, p is a factor of c0. We know that b0 and br are not the same because g has degree at least 1, similarly for the h's, and so p actually does divide b0 and c0, and so p squared must divide their product, which is a0. So we have that if everything else we assumed about f were true, other than this last, other than p squared not dividing a0, but f were reducible, then p squared would have to divide a0. Therefore, if f is irreducible, which was, or therefore if p squared does not divide a0, then that means that f is irreducible. Sorry, I'm getting mixed up. If p squared does not divide a0, then f is irreducible over the rationals. So let's take as an example, let's look at the polynomial 10x to the 7th minus 51x to the 6th plus 33x to the 5th minus 18x squared plus 12, and that belongs to z adjoin x. And so we can notice that the prime number 3 divides all but the leading coefficient, but we can notice that 9, the square of that, does not divide the constant term 12, and therefore f is irreducible in Q adjoin x by Eisenstein's criterion. And because f is primitive, that tells us that that f is irreducible in over the integers. So Eisenstein's criterion can give us a very, very fast way of determining that certain polynomials are irreducible. However, it does have to be a fairly special setup. Most polynomials do not submit to Eisenstein's criterion, but sometimes they do. And when they do, Eisenstein's criterion is absolutely the quickest and best way of handling those polynomials.